Hello, friends. We are here for your last lesson this week. This is on exponential growth and decay. So earlier this week, we talked just about exponential functions. And remember that we had that y equals a times b to the x, right? Where a is your starting point, and that's where x equals 0, right? That's your y-intercept. And then b is your common ratio. So exponential growth and decay functions are essentially very similar to that, except like your initial amount, right? So your starting point is the same. So again, that's where x equals 0. So you have a sub t or a of t, which we can call y, equals a, which is your initial amount or your starting point, times 1 plus or minus r, and r is your rate of increase as a decimal. So you'll often be given it in a percent, and you'll have to change it to a decimal first, and then you'll either add it to 1 if it's growth, or subtract it from 1 if it's decay. And then you're raising it to the t, which is like your x in this instance, but t is number of time periods. So like years or months or what have you. So all of this, like exponential growth and decay, we talk a lot with values. So this one right here, a sculpture is increasing in value at a rate of 8% each year, and its value in 2000 was $1,200. Write an exponential growth function to model this situation, then find the sculpture's value in 2006. So first we write our function, then we find the value in 2006. So A is your initial amount. Well, the original value in 2000 was $1,200. So that's our initial amount. The rate is 8%, but remember I said you have to change it to a decimal. So remember what you do with that. The decimal is on the right. You move it over to the left. So your rate is not 8%. It's 0.08 when you write the function. So your function is y equals 1,200 times, and I have to figure out whether I'm going to use plus or minus. Remember, if it's growing, I use plus, so I have 1. And then if it's decay, I use minus. Well, this is increasing in value, so it's going to be a 1 plus. So 1,200 times 1 plus 0.08 to the t. You can write that, or you can write 1,200 times 1.08 to the t. So just add the actual 1 and the 0.08. You can do 2. Then I'm going to find the value in 2006. So what you need to know, the only thing you need to know here now is what you're going to plug in for t. So t equals what? Well, the original value was done in 2000, and we want to know it in 2006. You're not going to raise it to the 2006 power. That would be 2006 years from now. What would the value be? You want it to know like how much time has passed between 2000 and 2006. So that's 6 years. So t is going to equal 6. So you're going to have y equals 1,200 times 1 plus 0.08 or 0.08 raised to the 6th. And then all you do is just go to your trusty graphing calculator, get the glare off of it. 1,200 times 1.08 raised to the 6th. And you should get y equals 1904.25. And it went from 249 to 25 because we're talking money, so we're going to round that to the nearest cent. All right, now if I want to graph these, I'm just going to graph one of them because really there's not a lot of graphing to be done in terms of growth and decay. But if you have y equals, let's put that in. So 1,200 times 1.08 to the x, right, or to the t. So I'm not going to hit graph because my window's all going to be all messed up. I'm going to hit second graph and get a table. So at 0, of course, I'm at 1,200, as I should know. At 1 year, I'm at 1,296. At 2 years, I'm at 1,399. I'm still not really close to, let's see. It's not until, well, 6, I'm almost to 20. So really what I should have done is go a lot further out here because right now it looks like it's a very slow growth. But it will start doing that. So that's really why we don't need to graph these that much because it doesn't always make a lot of sense for the problem. Okay. Original value of a painting is $9,000. Value increases, so 1 plus by 7% each year. Write the function, find the value in 15 years. Okay. So A, my original value of it is $9,000. My rate is 7%, but really 0.07. And then I'm going to use a 1 plus. So increasing or decreasing, it's going to be increasing, so it's plus. So y equals A, which is 9,000, times 1 plus 0.07 to the t, or y equals 9,000 times 1.07 to the t. So whenever it says write the function, it wants you to have this t or x or whatever in there. So then when you go to evaluate it, that's when you plug in for t. So this is saying find the value in 15 years. So t equals 15. Everything else is the same. So y equals 9,000 times 1.07 to the 15. Again, this is money. So you're going to want to round it to the nearest cent. 1.07 raised to the 15th. So this is $24,831.28. So it went from 9,000 and then in 15 years now it's 24,000, almost 25,000. All right, so that's exponential growth. Super duper easy peasy. The other one is exponential decay, and it's the exact same concept, except now it's a 1 minus. So the population of a town is decreasing, so that's 1 minus, rate of 3% each year. In 2000, there were 1,700 people. Write the function, then find it in 2012. Okay, so my function. So A is 1,700. My rate is 3% or 0.03. And is it increasing or decreasing? It's decreasing, so we're going to use a 1 minus. So I have y equals my A value of 1,700 times 1 minus 0.03 to the t. Again, you can always write this too as like having done the subtraction. So 1 minus 0.03 would be 0.97 to the t. Find the population 2012. Well, it started in 2000. So 2000 to 2012 will give you a t value of 12. So 12 years. So y equals 1,700 times 0.97 to the 12th. 1,700 times 0.97 raised to the 12th. And I get, all right, so here's an interesting thing. So now we're talking about people, right? So you can't have like, half a person. So because I'm decreasing, I'm going to put this up to 1180. And I know that sounds interesting. I would do that because it's a 5 anyway. But like if the population is going down like this, then I would get to 1180 before I would to 1179. Okay. If it's an increase like this, then I would go stop at 1179. So you kind of go to which one you would hit first, depending. So this is decrease. So I would hit 1180 first. So approximately 1,180 people. All right, fish population in a local stream was decreasing, so that's 1 minus, rate of 3% per year. Original population was 48,000. Write an exponential decay function, then find the population after 7 years. Okay, A is the initial value of 48,000 fish. The rate is 3% or 0.03. And is it increasing or decreasing? It's decreasing, so we use 1 minus. So my function is y equals 48,000 times 1 minus 0.03 to the t, or again, 48,000 times 0.97 to the t. Find the population after 7 years, plug 7 in for t. So y equals 48,000 times 0.97 to the 7th. Oops, sorry. Parentheses, 0.07 to the 7th. It would have done it just fine either way. I'm just used to parentheses. Oh, not 0.07. Clear. Sorry. 0.97. 48,000 times 0.97 to the 7th. I didn't read that carefully enough. Is, and again, I'm talking about fish. Can't have 0.17 of a fish, right? So because I'm decreasing, I'm going to stop at 38784, even though I know that doesn't make a lot of sense because like a 0.170 you wouldn't usually round it. But again, if I'm decreasing, I'm going to hit that one, like the 38,784 before I hit 38,783. Okay. So 38,784. Now, when you go to do this in Delta Math, I would, try that first, the 38,784. And then if that doesn't end up right, then do 783. Because they might not have the same sort of philosophy that I do on the rounding thing, or they might just expect you that you're going to round like normal. So try both of those and see which one works. Okay, last thing on here is something called compound interest. So to compound means to like apply the interest over and over again. So compounding how many times? Well, you could compound annually, which means once per year. So your number of times compounded would be 1. Quarterly, which is 4 times a year. So your number of times compounded or your n would equal 4. If it's monthly, it would be 12. If it's daily, which is sometimes, it would be 365, right? If it's weekly, it would be 52. So it's like the n is the number of times in a year that this happens. So this formula, which is really small to see, so I'll rewrite it up here. So it's A, but really I'm just going to rewrite this actually with my own letters. Okay, so y equals A is still your initial amount. They have that as P because that's your principal. Okay. 1 plus, it's always a plus because people are going to take interest away from you. They're always going to add it. 1 plus the rate over the number of times compounded, and then raised to the number of times compounded times the years. So this is a super similar formula to what we just did. The only difference is this n. So it's here and here. Otherwise, it looks like 1 plus r to the t, right? So it's just a compounding thing that we need to get in there. So you just have to make sure that you are careful the way you put this in. So I got to move the paper up. So I'm just going to rewrite this here. Okay. So write a compound interest function to model a situation, then find the balance after the given number of years. So $1,200 invested at a rate of 2% compounded quarterly for 3 years. Okay. So A, remember, is my initial value. So 1,200. My rate is 2%, but remember that's 0.02. The number of times compounded, it's quarterly. So I go back up here, that means 4 times per year. So n equals 4. And then the t equals 3, but that doesn't really matter until the next part because the t doesn't, remember, that doesn't go into the actual function. The t is your x value in this. So that's your variable. So y equals 1,200 times 1 plus my rate, which is 0.02, over my number of times compounded, which is 4, raised to the number of times compounded, which is 4, times my variable, which is t. So that is my function. And now I plug 3 in for t, and I put this in the calculator. So y equals 1,200 times 1 plus, oops, not plus plus. Let me start that over. Y equals, 1,200 times 1 plus 0.02 over 4 to the 4 times 3. Now, when you go into your calculator, my strong suggestion would be to multiply 4 times 3 first. I suppose you don't necessarily have to, especially if you're using a one that looks like this, but it might just be easier. So 1,200, 1 plus, and if you want to be all fancy, you can get a fraction in here, right? 0.02 over 4. You actually don't have to do that if you want to just put, 0.02 divided by 4. It'll do the same thing, so it'll follow order of operations. Raised to the 4 times 3, which is 12. And hit enter, and I got 1,274. And remember, this is money, so I round it to the nearest cent, which is 1. Okay. Now, next one, same thing, just different values. So I have $1,200 invested at a rate of 3.5% compounded quarterly for 4 years. All right. So A is 1,200 again. B is 3.5%, but 0.035 is a decimal. So even if it's already a decimal, remember, you still have to move it over, okay? N is 4 because it's quarterly. And then the 4 years, but we'll do that in a minute. So Y equals 1,200 times 1 plus 0.035 over 4 raised to the 4 times t. That's my function. And then when I put it in the calculator, it'll be 1,200 times 1 plus 0.035 over 4 raised to the 4 times 4, or raised to the 16. So 1,200 times 1 plus, see, I'll show you that you can just do it normal like this too without finding a fraction. Because again, remember, your calculator will follow this order of operations. So it'll do this division first and add 1. Raised to the 4 times 4, which is 16. So that balance will be $1,379.49. All right. Compound interest is used a lot in like savings accounts and that sort of thing. So like if you put your $1,200 in and it's a rate of 3.5% compounding quarterly, that's the amount of money that'll be in your account after 4 years. So you made $179.49 by doing nothing. So there you go. Save your money. All right. This is your optional assignment, practice B 11.3. I do want to, a lot of this if we like literally just did, right? But there is one that I want to show you, and it's number 9, because we didn't talk about half-life. Half-life is something you see in science a lot. A half-life means the amount of time that it takes to like become half of what it was, right? So in the half-life, your R is 0.5. Okay, so it says the half-life of iodine 131 is approximately 8 days. Find the amount of iodine left from a 35-gram sample after 32 days. So you'll put your R in as 5. So Y equals 35 times 0.5 to the 32. I feel like I'm missing part of that. I think there's something that has to do with days. Give me a second. So this will be, so remember you have like this E negative 9 means 8.15 times 10 to the negative 9. So that's how many grams or what have you will be in that sample. I'm just going to look up this real quick though, because I just want to make sure I'm doing the half-life formula right. I think I am. I'm almost. I wonder if there's something I have to do with 8 first. Quantity remaining, initial quantity of the substance, time elapsed, half-life, 1/2, 2/2, 1/2. Oh, that's what I didn't do. Haha, I knew it. I knew I was missing something. So, sorry, not to 30 seconds. So the half-life formula is Y equals your initial amount. So let's stick with A, and then 1/2 or 0.5 raised to the T over the half-life T. Okay. So that means like here it says Y equals, we had a 35-gram sample. So that A is 35, your half-life goes here 1/2. And then it's raised to the time, which is 32, divided by the number of days for a half-life. So 32 divided by 8, so that would be 4. So I would now put this in. This makes more sense. I'm sorry. So 35 times 0.5 or 1/2, doesn't matter, raised to the 32 divided by 8, which is 4. So that makes more sense. I'm like, boy, that looks like a lot less. So that is 2.1875. So that's how many grams is left after that point. Sorry about that. So there's your half-life formula. I think that's the only question on here, though. But you might get some half-life ones on the delta math. So that's how you do that. All right, that is it. Kind of a short and sweet lesson. Would have been even shorter had I not screwed it up. So there you go. All right, well, you guys have a good day. See ya.